My name is Sonia Lopez Alarcón. I'm a professor in computer engineering here at RIT, and I'm going to be introducing our next two speakers. So we have Jacques Carolan, who comes from MIT, right? And he's going to be talking about quantum photonic processors and machine learning. So please go ahead.
Cool. Thank you very much for the introduction. And let me open this guy up. Okay. I just need to. Full screen mode. I think this is it.
Yeah, but the projector. Oh,
okay. Cool. My name's Jacques Carolan. I'm from the Quantum Photonics group at MIT. And what I want to talk to you today is about quantum photonic processors. Okay, so these are reconfigurable quantum optical devices which can be reprogrammed for different applications. And in the first part of the talk, I hope to convince you that silicon photonics is a really interesting platform with which to implement these kinds of systems. Okay? And for the second part of the talk, I want to talk about some applications of these devices. And they're going to fall under the umbrella of machine learning optimization. And it's going to be twofold. First, I want to show you how we can use techniques from machine learning and optimization to control these complex photonic systems. And then I want to show you the converse, how we can actually use these large-scale photonic systems to actually accelerate both classical and quantum machine learning. Okay, so what is a quantum photonic processor? Well, a quantum photonic processor brings together three core technologies. On the input, you want to have some kind of non-classical light generation, and that's going to essentially encode the input to your computational problem. Then you're going to have some reconfigurable circuitry. That's going to encode the protocol that you want to implement. And on the output, you're going to have some kind of single photon detection. And that's going to encode the readout. Now, in terms of the hardware, there's a whole bunch of different ways in which you can do this. Okay? So the nice thing about photons is that you can either use them as a way to mediate interaction between long-lived matter-based qubits, which we're going to hear more about tomorrow from Dirk Englund. But what I'm going to focus on more today is actually using the photon as a qubit itself. Okay? And there are many different degrees of freedom which you can store information on a photon. We've heard some really awesome work from Jacques and the guys at Xanadu about how they can, use continuous variable degrees of freedom. What we're going to talk more about is the discrete degrees of freedom. Okay? You can have passive control in terms of the circuitry, using things like evanescent coupling to couple between adjacent waveguide modes, allows you to build things like on-chip beam splitters, or you can physically change the geometry of the waveguide itself, and that's going to allow you to do things like build on-chip filters. Okay? You can build cavities, build on-chip filters. It's also going to allow you to do things like enhance the interaction of the light with the material. In terms of active control, there's a whole host of different technologies you can use depending on the application that you want, right? So perhaps you want relatively slow but low loss modulation. You can use things like the thermo-optic effect, or you can use something like MEMS, or even some kind of electro-optic effect that will put you around the gigahertz regime. Finally, in terms of the readout, we have now really wonderful superconducting detectors. You can go to VICAS and, I believe, buy detectors that have 95% efficiency, which is really quite amazing. And of course, then you need to be able to outcouple from your chip with low loss. I think this is a problem which is beginning to get solved. In the literature, people have demonstrated sub-1 dB outcoupling. That's only going to get better. Okay, so I think this really is a problem we're going to have solved in the next year or two. Or if you're feeling really brave, you can try and fabricate the detectors directly onto your chip, okay? Or use some kind of flip chip technique. So what I'm going to focus on for the moment is just the circuitry side. And for me, at the core of the quantum photonic processor, it started in 1994, okay, with this beautiful paper from Reck and Zeilinger and colleagues. And what they showed is that if you have a particular configuration of reconfigurable beam splitters and phase shifters, you can implement an arbitrary linear optical operation across these modes. Okay? So the configuration they have in their paper looks something like this triangular configuration. Just to zoom in on it and to see how it's universal, what you can see is that, so each of these guys is now a Mach-Zehnder interferometer, and what you can see is that if you put light in this first mode, you want to get an arbitrary vector across these M modes. So you can jiggle this guy about and put the correct phase until you get the right amplitude and phase here, and then you can keep doing that. Okay? So the proof, what you can convince yourself is you can get an arbitrary vector out of this first diagonal. And the proof essentially precedes something like Gaussian elimination. So I like this paper for a number of reasons. I think the proof itself is beautifully simple and very elegant. I also love it because it's got the word experimental realization in the title, and there's no experimental realization. And part of the reason it was so hard to do this is that integrated quantum photonics wasn't really a thing back then in the early 90s. And what you can see is that you have a whole bunch of nested interferometers that require phase stability. So Michael Reck actually spent the majority of his PhD trying to implement this and wasn't successful. And my understanding is he then became a consultant at IBM. So part of me thinks this might be cursed somehow. So perhaps against our better judgment, in my previous group during my PhD in Bristol, we set about trying to build this. So what we came up with was a 6-mode universal linear optical device in silica using planar light wave circuit technology, okay? And now it's fully reprogrammable, so you can essentially go back through the kind of history books of linear optical quantum computing and program your circuit to implement, different operations. So we could do KLM controlled knot operation, we could herald Bell states, we could do quantum process tomography, okay? And the point I want to make is this is all on a single chip, okay? And this is really the advance that having these kind of universal reconfigurable circuitry offers. So what this showed is how you can go from something that is, say, meters in scale in terms of the optics bench to something that is centimeters in scale, okay? But that's still about the same size as my mobile phone using the platform of silica. And that's really about the scale of what you can do on a single wafer, okay? So the real question is, how do we get down to the millimeter or micron scale? Okay? And for me, the answer is silicon photonics. Okay? And the great thing about silicon photonics is you have an incredibly high refractive index contrast, which allows you to build very high density components, of the bend radius of the order of 10 microns. Okay? Now, your loss is going to be somewhere between 1 and 2 dB per centimeter, but the real metric that's important is your loss per component. And in terms of your loss per component, it really doesn't get much better than silicon. So I just want to give this beautiful example from Mike Watts' group. It's now a few years old, which is their phased array, where they have an array of 4,000 optical components, and it just kind of shows you the scale. The other nice thing about silicon is it opens up the possibility to integrate with CMOS electronics. We need to be very careful when we talk about this because, in my eyes, it's very unlikely we're going to start integrating all of our electronics into our photonic systems in the near term because you're probably going to sacrifice some of your photonic performance if you do that. But the option is there. And we also have a really nice chi-3 nonlinearity as well because we can generate new states of light. So at MIT, we set about trying to build a reconfigurable photonic circuit, and we came up with this. Okay? So it's in silicon, and it has 26 optical modes, and it has 90 Mach-Zehnder interferometers and about 180 low-loss thermo-optic phase shifters. Okay? Now, because we have this very high refractive index contrast and very small bend radius, the whole device is only about 5 millimeters long. So we've gone down in size by an order of magnitude, and we've gone up in complexity by an order of magnitude. And that just really shows you what silicon photonics can offer. Right? Just zooming in on the unit cell for a moment, this is what a Mach-Zehnder interferometer looks like. It's only a few hundred microns long. Part of the reason we can do that is because we have an incredibly efficient and compact low-loss thermo-optic phase shifter. So you can see that thermo-optic phase shifter in the middle there. Actually measuring the loss of this guy is pretty hard. If you put it in a ring, it doesn't really degrade the Q of the ring. But the really impressive metric that I find is that we see a 66 dB extinction ratio in this interferometer. So that's almost 7 orders of magnitude suppression going from your on state to your off state. Okay? Now, why is this interesting? Well, I'd like to borrow an argument from Terry Rudolph here, where he says that what this shows is that your Pauli Z error rate for photonics is at least 10 to the minus 7. Why? Well, if there was jiggling about on your phase shifter, you wouldn't see this extinction ratio. Okay? So I think that's a nice, there are many other types of errors in photonic systems, but I think that's a nice kind of heuristic there. So I've had to put this on a PDF, so I had some cool videos. So instead of having a videos, I've just put 3 screenshots of it in a row. So I'm just going to move through it quite quickly, and it's almost as if I've got a video. Okay, so what I'm actually showing here is that we put light on the input, and we've got an IR camera above it, and you can actually see the scattering. And this thing moves very quickly, and it's supposed to give you a kind of sense of the scale and the complexity of this system. But this isn't just for fun. We can actually use this to characterize and calibrate our devices. So what we've developed is a kind of overhead imaging system, which we can actually use to characterize things like ring resonators. So in the middle of this image, we've got a ring resonator, and as we tune the laser onto resonance, you start to see the thing glow. Okay? And what you can do then is just you pick a few pixels or average over some pixels, and then you get the resonance of your ring. Okay? So this was a really great visiting student, Ray, who did this. So this is actually a useful characterization tool for us. So now you've just got this really hard systems engineering challenge. Okay? We've got many optical modes going into this system, okay? 30 on the input, 30 on the output. How do you start speaking to this thing optically? We've had to develop custom interposer chips. We've done things in both laser-written waveguides and also in silicon nitride, which can both match your mode field diameter, get you down to the mode field diameter required for silicon, and also perhaps do some kind of unconventional spacing as well. And also in terms of the electrical control. Okay, this is a GDS layout of our electrical routing. Okay, this is a seriously complex system to control. So we've had to develop our own electronics, own custom electronics to actually control this system. Okay, so now that we have this highly reconfigurable silicon photonic device, the interesting question is, what type of applications can we do? Okay, so I'm just going to briefly mention 2 before I move on to the other part of the talk, and just 2 that are kind of close to my heart. One is in quantum simulation. Okay, so what the guys in our group looked at was how you can implement a discrete time quantum walk. Okay, and the way it works roughly is that you input your laser light here, and your photon moves across this way, and it has some equal probability to move left or to move right. Okay, and so that's a discrete time quantum walk. And what you can do is you can impart some random phase. Okay. And there's a feature in these kind of ordered lattices which is called environment-assisted quantum transport. And what you see is that as you increase your level of noise, you actually get an increase in your transport efficiency. Okay. So here you're a kind of Anderson localized regime. Here you get your environment-enhanced transport. And as you keep increasing, so this is efficiency, this is noise. And as you keep going even further, you basically get into a quantum Zeno regime. So you have this, what we call quantum Goldilocks effect. Okay. So this is a really nice platform which to explore it because you can do many operations relatively quickly. I should add, this is just a purely classical bright light experiment. So the interesting question is, what happens when you put multiple photons in? And there's a really beautiful result, which I was fortunate enough to be part of in my previous group, which basically asked the following. What are photons in optical modes? Well, they're non-interacting bosons. Okay, what other systems are non-interacting bosons? Well, phononic excitations of molecules are also non-interacting bosons. So if you put photons through these reconfigurable photonic systems, you've essentially got a simulator for any kind of non-interacting bosonic system. Okay, so in this paper, we looked at how you can actually, track the dynamics of different vibrational modes in these photonic systems. So it's kind of complementary to the kind of bosonic vibronic spectra we heard about earlier. And ask more about it if you're interested afterwards. And another thing that's dear to my heart as well is looking at quantum verification interference and inference. So this is a paper we're working on at the moment. It should be out in the next month, but the idea works something like this. There's more, people have realized that building a quantum computer is hard. I don't need to tell you all that. So a lot of the effort has moved toward these near-term quantum applications. Okay? And actually, they all look kind of similar. You have some input state, you have some kind of quantum circuit, and you ask, what is the complexity of drawing samples from this circuit? Okay? Whether you're looking at, for example, boson sampling, whether you're looking at random circuit sampling for superconducting, whether you're looking at QAOA, they all have this similar structure. So we wanted to ask a complementary question, which says, given access to these samples, can we figure out something about this circuit? Okay? So what we actually came up with was an efficient protocol to essentially find the inverse of the circuit. Okay? So this is applications in kind of verification and inference, and we actually implemented it a small-scale kind of proof-of-concept demonstration in our quantum photonic processor. Okay? So that should be out in the next month or so stay tuned, but it was a really fun collaboration between a bunch of different people, Seth Lloyd at MIT, Masoud Masheni at Google, and Johnny Olson at Zapata. So I want to get to the main part of the talk, which is how we can both use techniques from machine learning optimization to help control these silicon photonic systems, and how we can then use silicon photonics to accelerate machine learning optimization. So I want to take a brief detour into single photon sources, and I think we're going to hear about this in the next talk as well. But very briefly, one of the nice things about silicon is you can generate new states of light using the four-wave mixing process. It's got this chi-3 nonlinearity. So it has this kind of phenomenological Hamiltonian, right, where if you pump at some central wavelength, you can produce photons, or if you pump at these non-degenerate wavelengths, you can produce photons at a degenerate wavelength, and you can also have the converse non-degenerate process. And much of the field has now moved towards micro-ring resonators. Okay, so you have your bus waveguide and then a loop piece of waveguide above it, such that when the circumference of your ring is an integer number of wavelengths, you get these sharp resonances. Okay, what that essentially allows you to do is build up the field inside the ring and enhance the interaction of the light with the material. Okay. Now, the nice thing about this is you can have an incredibly small footprint of the order of tens of microns. Your generation rate is going to be proportional to the Q of your cavity, and it allows you to directly engineer your signal and idler frequencies. Okay. So there's this plot from Josh Silverstone's review paper that with just a few milliwatts of power, you can get to the regime of tens of megahertz on chip. Okay. So if we want to talk seriously about building large-scale quantum photonic systems, you're going to have to do something which looks like this, okay? You're going to have many single photon sources, and they all need to be aligned to precisely the same frequency. Why? Well, if there's variations in that frequency, there's going to be variations in the frequency of the photons, and that's going to reduce your quantum interference, okay? And that's going to cause logical errors in your subsequent computation, okay? And what types of things might cause this? Well, there's a whole host of different things, right? You know, one thing that might happen is that you can have, you might have crosstalk between different devices, you might have some kind of external noise source, you know, and especially as these rings are likely to be very high Q, that's going to place stringent demands on the control of your quantum system. Okay? So what we thought about was developing a feedback control system, okay, where you have your, you monitor the pump modes of the ring resonator, you monitor the photodiode, and then you feed back onto the ring. Okay? And the nice thing here, so you can see what the protocol might look like, you get some thermal noise, you monitor your power, you see it raise up, you correct that, and the power goes back down. And the nice thing is that can be performed in parallel to your quantum information processing. You never have to touch your photons. Okay? So I think that is actually a really awesome and unique point about photonics, and we mentioned this previously about doing all of your characterization and calibration with classical fields. Well, you can do this in situ, okay? You'll essentially be limited by your modulator bandwidth, okay? So that can happen incredibly quickly. And if you can distribute a single local oscillator across your entire device, this basically scales as a time complexity that's constant in the number of rings. So this is the chip that we wanted to look at for that. It's a quantum state engineering device where you put in, so it produces photons generally. You mix your two different pump colors on a directional coupler. You pump these guys in superposition, so you either get this one firing, producing 2 photons, or this guy firing, producing 2 photons. You then do some pump suppression just to get rid of a bit of your pump light to stop further photon generation. And then you can change the thermal optic phase shifter to move between your 2 zeros to your kind of 2 photon noon state and your 1 state. And just to kind of give you a sense of scale, in just a few hundred microns, we've got a whole bunch of thermal optic phase shifters, and they're all going to start coupling to one another. So it's going to be a pretty hard control problem. So what we did is we did some spectrographs to see the effect of, say, temperature changes or crosstalk. So we artificially changed the temperature of our tip in about 1 centigrade in a kind of quantum random, or in a kind of classical random walk. So you can see we have time here, and this is a spectrograph, and you can see how the thing moves. Okay, so it's shifting. We can also do it with the voltage of the phase shifter inside that interferometer. That shouldn't affect the position of the resonances, but you can see you get this change. Okay, so what we can do is perform our optimization protocol on this, okay, where we monitor the output and then optimize those rings to align, and you see the power drop down, okay, as you would expect. And importantly, the real metric is how good do we do? So what we can see, so this is when we apply this noise, we can actually get to a sub-picometer stability on those rings. Okay? And this is both for the kind of temperature error and this crosstalk error. So you might say, well, those errors that you showed, this looks like you might be able to fit some kind of model to it. So why don't you just fit a model to it and stop doing all of this malarkey with optimization? So we actually did that. We did the best model that we could do, and we still see about a 10-fold increase in stability using this in situ approach. So it really seems this in situ approach is the way to go. So we can do, I said they can do quantum state engineering, so let's actually try and see it. So here we're measuring the coincidences, and what we should see is this double fringe. We heard Stefan talking about it yesterday, and the pink ones are what we get if we don't apply this control technique, and the blue ones are what we get when we do. Okay? And we get a visibility of about 94%. That's still not perfect, and part of the reason is we have to do pretty aggressive filtering on the output, and that's causing a fair amount of loss. Another neat thing, which no one has really talked about in the past few days, is we look at the pump generation rate, we look at the photon flux rate as a function of our pump power, and you see it increase kind of quadratically. You're like, great, 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 and then it falls off. Okay? So the point is that in silicon photonics, we have 2 photon absorption, and this is why we see this guy level off. Okay, so that's a problem we need to overcome. There are ways to do that. Maybe you can move to longer wavelengths, but it's an important problem for silicon photonics. Okay, great. So in the final 5 minutes, I'm going to talk about neural networks. Okay, so I think it's fair to say there's been an explosion in deep learning over the past few years, which is essentially a computational model that is inspired by signaling within the brain. Okay, and it's seen exceptional performance in things such as image and speech recognition, language translation, and decision making. The way it works is actually pretty straightforward. Okay, what you do is you take some input data. Okay, say it might be some grayscale pixel values of some kind of image, and then that's this guy. And then you do some matrix multiplication that's parameterized by some weight matrix. And then you have some nonlinearity here, which is parameterized by some bias. And the aim of the game is to optimize those parameters to have a particular input-output configuration over some large vector set. Okay? So let's take a prototypical example, an important problem in machine learning, which is identifying cats. So what you can do is you can take all of your images of cats and you want them all to output cat, maybe the vector 1000, such that when you give it a new image of a cat, it will also output cat. It will do that classification. And there's a few reasons to think that this might be able to be done optically. Okay, first, optics is really good at matrix multiplication. That's what I've just told you about. Okay, so perhaps this core could be done optically. You could potentially get very high bandwidths, right? You know, we can have detection working at the 100 gigahertz regime, and if you can use some kind of set and forget architecture, something like Jacques phase shift or something similar, you can get an incredibly low power consumption. So a proof of concept demonstration of this optical neural network was done recently in our group in collaboration with Mariam Sludjic, and they show that you can do some kind of 4-vowel recognition task, okay? But I'm a quantum guy, and whenever I see something cool that is classical, my immediate response is, how the hell can I make it quantum? So we started thinking about this quantum optical version of this, okay, where now your input state is going to be Fock states, okay? You still have this linear transformation, and then you have some kind of single-site nonlinearity. Perhaps that's some kind of Kerr nonlinearity that's written like this. And on the output, you have some single photon detection. So how the hell do I get that nonlinearity? It's pretty hard. So one way you can do that is measurement-induced, such, a la KLM. Another thing which actually probably is more realistic is interaction with some kind of 3-level atomic system. Superconducting cavities also have a very high Kerr nonlinearity, and then potentially you could do some kind of all-optical tricks as well. But why the hell would you want to do this? So first, I think there's motivation just in terms of software. It might help you discover new types of gates which you didn't know the construction of before. But I also think in the lab, okay, it's our hope that we can somehow bring together the versatility of neural networks and the computational complexity of quantum systems. So it's worth exploring what this guy is capable of. An important point that I want to add here is that we've been inspired by photonics, but this doesn't have to only be implemented in photonic systems. There are many other interacting bosonic systems that could also do this. In particular, I think ultra-cold atoms is a really promising platform with which to implement it. You could also do it, for example, in the phonon excitations of ion traps, or even in superconducting resonator arrays. I just want to note quickly that this idea isn't completely unique. There's been a whole bunch of proposals in the past year when people have realized that building a quantum computer is hard. They've looked at these quantum neural networks. All of these guys are in a platform-independent manner, and there's a really nice proposal from the guys at Xanadu to do a similar thing, but in the continuous variable way. So in the last few minutes, I'm just going to talk about a few of the applications we looked at. So to train this thing, you need to define some kind of cost function. So what you want to do is you want to take some input states to some output states, and that's going to be your cost function. This is described by some system. So you want to optimize and minimize this cost function using your favorite numerical technique. We actually found there's a whole host of stuff in the NLOpt library, and this particular one worked very well. So the first thing we want to check is, can it do all the things that we think that it should be able to do? We've given it the power of a strong Kerr nonlinearity. It's sure as hell better be able to do controlled knot operations. It better be able to do, prepared GHZ states. And that's what we looked at. So what we're doing here is we're increasing the layer depth of this system, and we're seeing that as we increase the layer depth, the fidelity, the success of us being able to find this controlled knot operation or GHZ state increases. Okay? And this is actually something that we see in classical neural networks as well, is that as you make the thing deeper, it increases the expressibility of the system. Okay? Now, of course, if you get too deep, that becomes very hard to train, so you're looking for this sweet spot. But this is something people know how to do well in classical neural networks. But neural networks do something much more than that. Okay? Neural networks do something more than that. They generalize over inputs that they haven't seen. What we've done there is just feed it in the basis set. We want to do something that we want to generalize over things it hasn't seen. So in the final just 30 seconds, one thing we looked at was black box simulation. Can we get the system to implement some Hamiltonian of interest? We looked at Ising models. We looked at Bose-Hubbard Hamiltonians. It does a pretty good job of those things. And we also looked at a new data compression algorithm, a quantum data compression algorithm called the quantum optical autoencoder. And that's going to be important for some communication protocols. And what you essentially do is you compress your state in some large space down to a smaller state. Okay? And we showed that we could do that optically. So if it's not totally clear, this was all numerical simulation. Okay? And finally, we looked at how well our quantum optical neural network could balance a pendulum, a classical machine learning task. And what we could actually show, so this is the number of generations, okay, and we built this reinforcement learning system. We could show that as we increase generations, we can actually balance, we can learn the laws of physics with this quantum optical neural network. Okay? And the reason I think this is important, we don't know if there's a speed up. I'm not claiming there's a quantum speed up in this, but we can give it real classical data and it will learn on that. So it's an important step forward. So the final thing we're going to look at with this now is whether we can learn, for example, loss correction code. We've got some really nice results about that at the moment. So I'm out of time, I'm going to wrap up. I've showed you some of the hardware we're looking at, how we can use techniques from machine learning optimization to control this complex hardware, and then how we can use that hardware to accelerate both classical and quantum systems. Okay, thank you very much.
So one of the main issues for multi-layer perceptron and neural network are the initialization of the weight, because they are usually randomly initialized and that can converge to different solutions. Is it an issue in your structure and how you deal with that?
Yeah, so this question of training is, there's so many elements to that, and I could talk about this for ages. There's a field recently so traditionally in classical neural networks, they just look at real matrices. And what you find is this problem which is called the vanishing or exploding gradient problem, okay, which is as you make this thing much deeper, it becomes significantly harder to train, okay, because these gradients explode or just become infinitesimal. So people have started to look at, just in the classical world, of using unit trees instead, which have this kind of, which behave much nicer, which get around this problem. So there's a whole bunch of interesting research in the classical, and I think it's interesting whether it applies to our system. That's still an open question yet. One thing we have developed is actually using some kind of autograd code, using auto-differentiation to actually calculate gradients, and that speeds up our training significantly. The real question is, like, when we actually do this thing in situ, how are those gradients going to fare? Are they going to disappear? And that's an open question for the whole field of quantum neural networks. But I believe there are a whole bunch of different tools and heuristics that we can borrow from the classical neural network community, which will help that in practice.
What's the bottleneck? What's the biggest bottleneck? And if it's the sources.
Yeah.
If it's the sources, what's your view for what the sources will be? Dots, parametric sources?
Yeah. I think that's a really interesting question. It's lucky you asked that, because I've got this wonderful slide. What I am really fascinated in, and I mentioned it in the panel talk, is how we can add things that aren't in the Foundry process into Foundry systems, okay? So the big thing, of course, is nonlinearity, okay? How do we get a strong Kerr-based nonlinearity? Well, it's really hard. But there are other systems that exhibit very nice nonlinearities. For example, quantum dots have this incredibly high scattering nonlinearity, which is a bit weird. It allows two photons to pass through, but it reflects one photon. It puts that into some different optical mode. I think it's really interesting whether you can use those types of things, and that doesn't require strong coupling as well. They already have these working up to 60% efficiency or so. So I think it's fascinating whether we can use that in these types of systems. So I think for me it's the nonlinearity, and of course if you solve the nonlinearity problem, you're probably solving the photon generation problem at the same time. I guess a lot of the tools are similar, and it's getting those into a system that we can use.
So beyond parametric, though?
For me, yes.